So I ask you, how many of you ever heard of something called a cycloid? Well, at least one person had to say yes, right? A cycloid. You guys, you remember what it was, Eric? How do you get it? How do you create it?
Like to go in circles and then region.
That's right. And we're tracing that point through space, right? Okay, so we're going to draw an axis here, okay? So we can pretend this thing is rolling along the x-axis. And what we're going to do is we're going to start with a circle right here. Okay? And this is going to be our point of interest right there. This is going to be the point that corresponds to t equals 0. Okay? So what happens is that this circle is going to roll. It's going to roll in this direction, like that. And as it does, as it rolls, we're going to do what Eric said. We're going to pay attention to where this dot stays as the circle rolls. Okay? So would you agree after it rolls a little bit, it's going to look like this? This dot will have come up the side of the circle a little bit? Okay. You know how to derive it? Okay, cute. So then, yes, that's going to be the idea. That's right. So my goal here, let's state my goal and be clear about this. My goal is going to be, we're going to find a parameterization for the cycloid, for this point that we're riding along. So I mean, you could sort of imagine this in some goofy way. You know, a car's driving down the road. It runs over like a sticker, right? And the sticker sticks to the bottom of the wheel. And as the wheel rolls around, the sticker sort of cycles around. And the question we're interested in is, how high is this sticker above the ground at any point in time? This mark on the tire. So we can start to figure it out that, you know, the path's got to start to look like this. At some point, it comes back down. And then at some point, it's actually like almost down to here, touching again. So you end up with this path for the sticker, for this point along the circle. And do we agree that it's periodic? Right? We should expect now to see a copy of that. Okay? And that green curve there is called a cycloid. Okay. So the claim of the day is that we can get the equation of this pretty easily if we just think about the right vectors. Okay? And then you'll tell me what you think when we're all done. All right, so we're going to start again and draw a new picture. You sort of know about what this thing's doing. So let's imagine the circle has rolled a little bit away from the origin, and this point here is where we are. Okay? I'm going to call that point P. Okay. So, what I'm interested in is the vector that starts at the origin and points at P. So I'll call the origin O. We're interested in vector OP. That's what we care. And then you'll notice, Jerry, I'm putting arrows on top today. I told you I would change things up. Okay. So what I'm going to do is I'm going to draw a picture of some other vectors that would add to this vector. And you might say, well, gee, why are you picking those? And hopefully I'll convince you later on that this was a good choice. Okay, so there's a center of the circle here. I'm going to call that point C. There's a vector that points from C to point P. There's definitely a vector that does that. There's another vector that points from the x-axis up to C, such that blue vector is perpendicular to the x-axis. I guess we'll call that maybe M. Okay? And then lastly, there's a vector along the x-axis that points from O to M. So there's that vector there. So here's a true statement. The vector OP is the sum of vector OM. So if I moved the way OM told me to move, then I added to that MC, right, I would get to the center of the circle. Then I added CP, I would get to the point that I want. This seems like a lot of work. Okay? Any questions so far? All right. So, let's look at all three. Our goal is going to be to figure out a way to write all three of these vectors. So, I claim one of them is easy to write right off the bat. Doesn't require too much thought at all. That's vector CM, or MC. If you look at vector MC, does it change at all in the x direction? No. So you can write that 0i. Now I have a question. Have you seen the x times I plus y times j notation for vectors? Okay? Yes or no? All right, so we're going to have to deal with that. You haven't seen this notation? Okay, so we need to talk about that briefly. Let me just finish this. Plus, j there. How far up does this thing go? What's it related to in this picture? Good. So we're going to call that r. So I just need to make that clear. We're going to say here on the bottom, let little r equal the radius of our circle. Okay? So far, we've got one of the vectors right away. That was pretty quick. All right, so I need to come back to this in a minute. I just need to briefly review the meaning of this notation with the I and the J. All right, so I'm going to go to a new page for a second, and I'll come back to this picture. Okay. The vector I stands for the vectors 1, 0, and the vector J stands for the vector 0, 1. I'm showing you this because what this means is we can take a vector like 3, 4 and write it in a new form. We can think of it as the scalar 3 times this vector 1, 0 plus the scalar 4 times this vector 0, 1. Now let's make sure that really makes sense. We talked about vector operations yesterday. If you just reviewed it, you kind of know about them. But if you distribute this scalar into this vector, that vector becomes the vector 3, 0. Plus, distribute the 4 into this other vector, this becomes the vector 0, 4. And then we add our vectors component-wise, and we get the vector 3, 4. Okay? So what does that mean? Well, it means that when you see a vector like 3, 4, you have the option of representing it this way. 3 times I plus 4 times j. That's what that notation means. Okay? These two vectors are very special. The I and j vectors are called the unit basis vectors. So later in the course, we'll discuss what it means to change basis vectors. It's a whole bunch of stuff in linear algebra that we don't talk about, but I'll talk about a little bit of things there. A few of the ideas from that course. Okay. Let's go back to our picture. So now this has meaning. Okay? All right. The next vector I'm going to attempt to go for is vector OM. Okay. So I think what would help us in finding vector OM would be to look in this picture for another distance that would be the same as OM's length. And it's sort of fun, but if you think about the circle rolling, so I would love to have another color, I don't. But basically what you know is this. Arc PM, that distance along the circumference, has to equal the length of OM. That's the section of the circumference that we've traced out along as this wheel has rolled. Now we're going to assume this wheel doesn't slip at all as it rolls. That's the case. Okay? So we know that then. All right. So I'm going to give a name to something, and then all of this will become much better. So I'm going to name the angle between these vectors here. I'm going to name that angle, angle T. All right? And I need to go back in time, pretty far back in time, to when you first learned about angles and radians. Right? And maybe it depends on what your teacher said to you at that point, but maybe you learn theta equals S over R, where S stood for arc length, and R stood for radius. Maybe that's what you learned. Okay? Or maybe a teacher just wrote S equals R theta. You know, and that's just an equivalent form of that equation. Okay? So, that being the case, we know this equation is true. We actually know how long that arc is. Arc PM, right, has a length, has a distance. What does it equal? Well, if we use this formula, the arc length is the radius of the circle times the angle. So we said the radius of the circle is R, and we said the angle was T. All right? So it turns out we can use this fact to get one of the components of vector OM. So we think about vector OM, it changes in only one direction. It only changes in the x direction. It doesn't change in the y direction at all. So since it doesn't change in the y direction, I instantly go over here and say plus 0j. And then over here, well, we just figured it out, right? We move the distance of r times t along in the x direction. So it's r t times I. Okay. We're on our way. This is looking pretty good because now I have two of the vectors that I'm going to need. I just need one more. So we have two of the vectors. I'd like to get that third vector, PC. So what I want you to imagine is we're going to take this section of the graph here, and we're just going to make it a little bigger. We're going to remove it from the picture. Let's do that. I'll redraw it. Here's that circle. Here we are. There's the point P. Here's O. Here's C to P. And that's the vector that I'm looking for. Okay. So I want you to imagine what we're going to do is we're going to drop an axis down on top of this circle in such a way that the origin of that axis lands on point C. And I'm doing this because this gives me something I'm very familiar with. I've also would like to remember, I'd like you to remember, we named this angle here. We call that angle T. Didn't we? Okay. So, watch. Here we go. Here's the axis one more time. I'm dying for a right triangle. I want a right triangle because I know lots of stuff about right triangles. It turns out I have one. Here it is. Here's the angle T up here. And if we're careful, we realize, hey, the components of the vectors are here. That's the x component of the vector that I want. Excuse me. That's the y component of the vector I want. Right? And if we really think about it, we know how long PC is. All right? It's the radius of a circle. So this has length r. You ready? So what does x have to be? Well, we look at this angle T. Opposite T is x. The hypotenuse is r. So we can say that the sine of T equals the opposite over the hypotenuse. Or x equals r sine T. Now, I need to just be careful. All right? Because would you agree I'm moving along the negative x-axis? Right? Aren't all these x values over here negative? Like this vector here moves backwards, moves that way, and then it moves that way. So it has a negative x value, and it has a negative y value. So I need to negate this. All right? Then we have one more fun thing to do. Y, via the same reasoning, this y value would be adjacent over hypotenuse. It would be y over r, so we cross multiply or multiply group by r. You get r cosine t, and that would also need to be negative for the same reason. So now we're set. We actually know vector CP. So vector CP is equal to negative r sine t I plus negative r cosine t j. Okay? So that's what that is. And here's the beautiful part. Now we just add these things together and we get an equation for the cycloid. That's all we had to do is add these things component-wise. Right? So let's go back to the first page we had with all these things. Ready? Here's the original picture. So OP, this thing right here, is going to equal OM plus MC plus CP. Okay. So I'm going to ask for help just to remember all these things. Okay? So here we go. It's OP equals. So it's going to be something times I plus something else times J. So if we add all three components, we look at them. MC has 0I, so it adds nothing to the X component. Then we have an RTI to add, right? And then, because of this other problem, we have a negative R sine t. So this first component is RT minus R sine t. Okay, good. Let's go back and go for our Y component. Well, MC contributes R to the Y component. Vector OM doesn't contribute anything. And then this vector, negative R cosine t, gets contributed. So let me just make sure my memory is okay. So R minus R cosine t. Okay. And if you take a look at this, some things I'm not really surprised about. I'm not surprised that the component y here, if you look at it, has a periodic function in it. Because if we think about our cycloid as it rolls, right, y starts in the bottom. At some point, y reaches a maximum height, and then down near the bottom again, right? So we expect these things to happen. In the same sense, I guess this component's a little bit more difficult to think about, but what's happening? This first part, this RT, sort of keeps us moving forward. It's saying, hey, look, as time gets bigger, right, R times T gets bigger, so it's going to move us to the right. This is saying sometimes we're going to get pulled back to the left a little bit, and then we'll get pushed forward even faster to the right. So we sort of, that's sort of what that's saying. Okay? Record that for our thing. It's going to be part of it. There you go. There's your animated cycloid. That's pretty neat. All right, well, I hope you enjoyed that.